Hi everyone, thanks for listening into this talk. My name is Richard, and today I'll be discussing work done by myself, Mohammed Javad Hojaste, Aaron Ames, and Joel Burdick on achieving safe multi-agent interaction through robust control barrier functions with learned uncertainties. Today, we have excellent centralized and decentralized robotic systems that can safely coordinate many robots in structured environments. On the left is a picture of an Amazon warehouse with several Kiva robots navigating around each other. But as robots become increasingly prevalent in our society, they will have to learn to safely navigate also in human environments with high uncertainty, like the terminal you see on the right. Even in these uncertain situations, some formal guarantees of safety will be critical in order to avoid harm to people and encourage wider acceptance of robots. In this work, we aim to guarantee safety of robot controllers in multi-agent settings by utilizing robust control barrier functions that can efficiently incorporate learned uncertainties. Here's an outline of the talk. First, I'll give some background on control barrier functions and then briefly describe multi-agent CBFs that can be used to guarantee safety in multi-agent settings. I'll then discuss how to incorporate robustness to uncertainty in these CBFs and how we can accurately learn bounds on these uncertainties. I'll conclude by showing some of our results obtained in simulation. So first, let's go through some background on control barrier functions. Let's first consider a safe set C defined by the superlevel set of a smooth function h. The safe set C is everywhere that h is greater than 0 and could denote all states from which collision can be avoided, for example. For safety then, the challenge is to ensure that set C defined by h is forward invariant. Now we say that the function h is a discrete time control barrier function with respect to the control affine dynamics shown here if this condition on the right is satisfied for all states x in C. And intuitively what this means is that if we can compute U that satisfies the condition for all states in C, then we are guaranteed a safe controller, or forward invariance of C. If you look at the top figure on the right, if a proposed controller U1 would take us along the unsafe red trajectory and crash, then the CBF would allow us to find the minimally invasive controller U2 that would keep us within the safe set C. Suppose you're given a potentially unsafe policy or feedback controller you proposed. Then by solving the optimization problem on the right, which incorporates the control barrier condition as a constraint, you can filter your desired control action to the closest safe control action. In the policy space, this looks like projecting the proposed controller into the set of safe controllers, as shown in the figure on the left. Therefore, given the full system dynamics and the control barrier function h, we can guarantee system safety by solving the described optimization problem. The questions this talk focuses on then are 1. How should we define h in the multi-agent setting? 2. How can we be robust to uncertainty in dynamics? And 3. How can we infer such uncertainties? So first, let's focus on defining h in the multi-agent setting. Borman in a 2015 IFAC paper proposed the multi-agent control barrier function very similar to the one shown in the top left for multi-agent systems with continuous linear dynamics. And they showed that indeed h of x is a valid control barrier function that can be utilized to guarantee safety. And the intuition was that this multi-agent CBF ensured that our agent could always match other agents' velocities before a collision would occur. And we show that this control barrier function can also be used for discrete time dynamical systems. Furthermore, with strict assumptions of the dynamics, which ensure that the agent can accelerate in any direction relative to other agents, h of x is a valid discrete time CBF for a restricted set of control affine dynamical systems, with a max in the control barrier function defined as you see at the bottom. Now that we have defined a control barrier function h that we can use, how can we ensure robustness to uncertainty? So consider the control affine dynamics at the top right, where f and g are known, but d is unknown or uncertain. Now given our control barrier function on the left and the corresponding control barrier condition on the right, we essentially want to filter our proposed control action such that for all D in a set of possible disturbances, the control barrier condition is satisfied. And this is encapsulated in the optimization problem at the bottom left, and this guarantees robust safety under uncertainty. However, the two key issues we must address are: one, how can we efficiently enforce this CBC constraint in the optimization problem? And two, how can we accurately capture this set of uncertainties D? With regard to the first issue, let's take the described optimization problem at the top left, which guarantees robust safety. And let us first derive a bilinear lower bound on the control barrier condition, as shown here. You can find further details on this in the paper. And second, let's assume the uncertainty D can be bounded in a polytope as shown here. Then the optimization problem can be restructured as shown at the bottom. So any solution to the optimization problem at the bottom is guaranteed to satisfy the control barrier condition. Now this is still a difficult optimization problem because we still have to optimize over all D in a polytope. But we show that this optimization problem on the left can be equivalently reformulated into the quadratic program on the right. Therefore, if the uncertainty in our dynamics D is bounded in a polytope, then the control action obtained from solving the optimization problem in green robustly satisfies our original control barrier condition, rendering the set C forward invariant and guaranteeing safety. Now that we've shown that we can incorporate uncertainty into our control barrier function, the next question is, how do we learn bounds on this uncertainty? And for this, we turn to the popular Gaussian process models. These models allow us to estimate our uncertainty D based on data or observations gathered. You can find further details on these models in the references I've listed at the bottom, but essentially, they allow us to model D with a mean and an uncertainty, thereby allowing us to bound model error with probability 1 minus delta for some desired delta threshold. For example, in the figure on the right, the blue bars denote a confidence interval we can infer for the function based on observations depicted by the red dots. In this work, we utilize the multivariate extension to these Gaussian process models, since our uncertainty is typically multivariate with potential dependencies between the different elements of the uncertainty. And this gives us a useful quadratic bound for our uncertainty, which you can see on the bottom right. The process we follow then is to first train a multivariate Gaussian process offline to obtain accurate model hyperparameters, and then obtain online estimates of the mean and covariance of our uncertainty D. The purpose is to be able to obtain a Gaussian distribution over D so we can bound it with probability 1 minus delta. You'll note that this is a quadratic inequality, thereby giving us an ellipsoidal bound, and not the polytopic bound that we desire. The solution we consider is an extremely simple one, in that we just find the minimum bounding box for our ellipsoidal uncertainty as depicted on the right. Therefore, if we suppose our robot and environment uncertainty is accurately captured by our multivariate GP, then with probability at least 1 minus delta, we can obtain polytopic bounds on our uncertainty D based on the eigenvalues and eigenvectors of the inferred covariance matrix, as described in the lemma on the left. Putting all this together, we can finally provide overall probabilistic guarantees of safety in the form of the theorem on the right. And this is done by incorporating our learned polytopic bounds into the quadratic program at the bottom left, which, as discussed earlier, guarantees robust satisfaction of our control barrier condition and therefore robust collision avoidance between agents. Finally, I want to conclude by showing some simulation results using this approach. So we set up randomized environments where we had a blue agent with a randomly initialized start position try to navigate to a randomly set goal point denoted by a yellow star. And it had to safely navigate among uncertain red agents with differing behavior who would move towards some unknown goal position. So in this first video, I'll show the blue agent is using the nominal multi-agent CBF. You can see it is able to navigate to the yellow star, but it does have a slight collision with one of the red agents. Now in this second video, the blue agent is using the robust CBF described in this work. And you can see it takes a more conservative approach by first stopping, but it is successful in getting to its goal without collision. Now, this is only a single instance, but we performed simulations in 1,000 randomized trials and found that the collision rate decreased substantially by incorporating uncertainty about other agents' behavior into our multi-agent CBF. You can find these statistics in the table in the top right. To summarize, this work has dealt with guaranteeing safety in multi-agent settings by developing robust multi-agent CBFs that will incorporate learned multivariate uncertainties. But I think there's much future work to be done in this space, and so to conclude, I want to note two prevalent issues that we are very interested in exploring right now. The first being, for many applications, Gaussian processes are not sufficiently accurate in modeling uncertainty. So we need better predictive models and uncertainty parameterizations. Second, for more complex robot dynamics, we may need to learn a more complex multi-agent CBF-H that may be less conservative and more suitable to a specific robot's dynamics. So that concludes my talk. I hope you'll check out the paper, and thank you for your attention.